All right, guys, welcome to our first lecture here. It is on atomic theory, which is going to lead us to a discussion of isotopes and mass spectrometry. The basic idea here of this lecture is based upon the idea that John Dalton put forward, which is that there are atoms in the world. Now, while today this does not seem particularly controversial, back in the day, this was a big deal. People didn't believe in atoms, and it wasn't until Dalton came along with quantitative proof that people actually began to believe in these things. And Dalton's atomic theory was based upon 5 different basic ideas. The first of which is that, okay, all matter is made of atoms. Those atoms are indivisible and indestructible. They are identical of a particular type, so all sulfur atoms are the same, all uranium atoms are the same, all hydrogen atoms are the same. And then you actually make a compound when you take 2 or more different kinds of atoms and put them together. And then if you have a chemical reaction, that is simply a rearrangement of those atoms that are there. Now, these are the 5 basic ideas, but it turns out that 2 of them are kind of slightly not true. Take a moment and pause the video and see if you can look at these 5 and determine which of these 5 are not actually true. There's 2 of them. All right, assuming that you have unpaused and are back, the first of the 2 that's actually not true is number 2 here, that atoms are indivisible and indestructible. We know this now because we know that inside atoms there are smaller particles, and those particles destroy the idea that atoms cannot be destroyed. So Dalton's idea was that's what an atom looked like. It was a tiny little sphere that was indestructible. But we know now that inside atoms there are little things called protons, neutrons, and electrons. And it's those protons, neutrons, and electrons that really tell which atom it is, what mass it is, what charge it is, and it gives it all its different properties. And if we wanted to go further, inside protons, neutrons, and electrons are things called quarks, and you can even get smaller than that. But then we're getting into well beyond the scope of what we need to cover in this particular class. So just know that basically the idea here is that atoms are not indivisible and indestructible. They can be broken apart in nuclear reactions and so forth, but for the most part, we're not going to deal with that. We're going to stop at protons, neutrons, and electrons. Now, what's the other one of these 5 that is not actually true? And it is actually number 3. All atoms of a given element are identical in their mass and properties. That is not actually true because it turns out that even for most atoms, there are 2 or 3 different types of that atom that are slightly different from each other, and those things are called isotopes. And almost all atoms have at least 2 isotopes. There are a handful of atoms that have only 1 isotope, but most atoms have at least 2, if not more, isotopes. The element tin, Sn, has 10 different isotopes. So it can get pretty complicated. Now, how do we know this? Well, we know this for a variety of reasons. But the isotopes are different because of what is inside of those isotopes. So the isotopes of carbon, you'll notice, are all the same because they have 6 protons. That's the atomic number of carbon. But they are different because they contain different number of neutrons. So carbon-12 here contains 6 protons and 6 neutrons. Please note that the 6 protons and 6 neutrons go together, add up to make 12. 6 and 6 is 12. Carbon-13 is carbon-13 because it's 6 and 7. Add those up and you get 13. And carbon-14 is carbon-14 because 6 and 8 go together to make 14. So please note they all have the same number of protons, which is why they are carbon, but they all have different number of neutrons that are there. Now, how do we know this? We know this for a variety of reasons, but not the least of which is that we have developed technology called mass spectrometry. Now, this can get awfully complicated awfully fast. But in this diagram, this basically shows what's going to be happening here. You're going to insert a sample into this. It's going to ionize and be sent through a magnetic field. And then that magnetic field is going to bend the isotopes And based upon their different masses, they are going to show up at a different spot on a collection screen. This next picture perhaps does a better job of showing that. Your gas sample enters here, right, and it is ionized through the application of energy. Those samples are then sent through our magnetic field that is right here, and that magnetic field bends the path of the isotope. And if it is of one mass, it is bent a certain amount. If it is of a different mass, it is bent a different amount. So because of the different masses, they will show up at a different spot on this detection screen over here. And that can all be mathematically figured out and backworked if you know a whole lot about the charge and the mass and a whole lot of geometrical math and so forth, none of which you're going to actually have to do. The point is that after we apply this theory, you will end up with a graph that looks like this that shows, okay, so there was an isotope of mass 92 and it was this abundant, an isotope of mass 94 and it was this abundant, and so forth and so on. Right? Now, if none of that made any sense, let me show you a video, and hopefully that video will do a slightly better job of explaining what's actually going on in one of these kind of devices that's here. So this is a video that I made with my kids, and what it is this. Here we go. So let's check this out. So over here we've got an atom being introduced into our, quote, magnetic field. That's just a couple of fans, right? So you notice I'm throwing these guys in. But wait, oh, that one is deflected a little less. So, and then that one is deflected a lot more. So as we're throwing these atoms into the magnetic field, which is, again, just a fan, they are being deflected by different amounts. And you can tell that they are of different masses based upon how much they are deflected. Some of them are deflected a lot, some of them are deflected a little, and so consequently, because they are of different masses, you end up with different separations of them that's there. Now, there's a couple of things that we can determine through this experiment. First of all, we can determine that there are 3 different isotopes of this element. There is an isotope that is heavy, there's an isotope that is medium, and there's an isotope that is large that's there. And we can tell that there are different amounts of each of those isotopes. So our mass spectrometer will collect our data. The question is now, how do we take those different isotopes and combine them so that they are all together into one box? Because there's not 3 different boxes for this element on the periodic table, there's only one box. So which of these am I supposed to put? Am I supposed to put the heavy ball's mass up there? Am I supposed to put the light one up there? Which of these numbers am I supposed to put up? Because they're very different. This one is 206, this one is 46, and this one is 32. Which one of these numbers is supposed to go there? Now you might say to yourself, well, why don't we just average all of them, right? Take the 206, the 46, and the 32 and add them up and divide by 3, and that's the number that goes there. And that's not a bad thought, except you're forgetting the other aspect of what the mass spectrometer taught us. Not only are there different masses of them, but there are different amounts of them. Remember that this one, there were only 4, and in this one, there were a lot more over here in this pink one, right? So we're going to have to take those into account as we do this. So for the large one, we only had 4 out of the total. For the smaller one, the lighter one, we had a bunch out of the total. So what we're going to have to do is we're going to have to take into account their percent abundance. So there were 4 of those, there were 9 of those, and if you add up here, 1, 2, 3, 4, 5, 6, there were 6 of these guys, right? So 4, 6, and 9. So the 206 is bigger, but it's less important because there's only 4 of them. The 32 is lighter, but it's more important because there's 9 of them. So we have to take both of those factors into account. So the first thing that we're going to do is take these numbers and we're going to turn them into percentages. So a percent is just a part out of the total. So 4 plus 6 plus 9 is going to give me 19. So then 4 out of 19 and 6 out of 19 and 9 out of 19 will give us, respectively, 0.2105. It will give us 0.3158, and it will give us 0.4737, or it will give us 21.05%, 31.58%, and 47.37% of those guys that are there, right? So we're going to take those decimalized percentages that we got here, and we are going to combine those decimalized percentages with each of our masses. So this guy here, what we're going to do is we're going to take 206, but only 21.05% of them are the 206, so that's going to be its fraction. So I'll simply multiply them together. Take the 206 and multiply it by 0.2105. When you do that, you get 43.363. Now we're going to take this one and we're going to take the 46 and we're going to combine it with the 0.3158. And when you do that, you get 14.527. And then for this one, you're going to take the 32 and you're going to multiply it by its fraction, which is the largest of the three fractions, 47%, 47.37%. And when you do that, you end up with 15.158. That's there, right? Now all we have to do is add up each of these fractions. And if we add up all three of these fractions, we get a total of 73.048. And that is the actual average atomic mass. That is the number that goes here on the periodic table for this mythical element. That number would be 73.048, right? Which is a very different number than if you simply add them up and divide by 3. If you add them up and divide by 3, you don't even get close to that number. So what you're going to have to do for each of these isotopes is take into account each of their masses of the different isotopes and each of their abundance for each of their isotopes, and then add each of those fractions up. If there's 2, there's 2. If there's 3, 4, 5, up to 10, this is your general formula here. So isotope 1, you multiply its mass times its abundance. Isotope 2, you multiply its mass times its abundance, and then you add them together if there's only 2 isotopes. If there's a third, then you add the third and the fourth and the fifth and so forth. And this is how you arrive at the number that is on the periodic table for the average atomic mass, taking into account the fact that there are different isotopes with different masses and different abundances of those different isotopes.